What is semiconductor material? A semiconductor material is a type of material that has electrical conductivity between that of a conductor, such as metals, and an insulator, such as non-metals. In other words, semiconductors exhibit moderate electrical conductivity, which can be controlled and modified through various external factors like temperature, light, and voltage. The behavior of semiconductors is crucial in the field of electronics, as they form the basis of many electronic devices and components, including transistors, diodes, integrated circuits, ICs, and more. Semiconductors are typically crystalline in structure, and their electrical properties can be manipulated by introducing impurities or dopants into the crystal lattice through a process called doping. There are two main types of semiconductor materials. Intrinsic semiconductors. Intrinsic semiconductors are pure semiconductor materials, such as silicon, Si, and germanium, Ge, in their natural state. These materials have a balanced number of electrons and holes, electron vacancies, and have limited electrical conductivity at room temperature. Extrinsic semiconductors. Extrinsic semiconductors are semiconductor materials that have been intentionally doped with impurities to alter their electrical properties. There are two types of extrinsic semiconductors. N-type semiconductors. These are created by introducing elements with extra electrons, such as phosphorus or arsenic, into the crystal lattice. The extra electrons become majority charge carriers, making the material more conductive. P-type semiconductors. These are created by introducing elements with fewer electrons, such as boron or gallium, into the crystal lattice. This creates holes, electron vacancies, that act as majority charge carriers, contributing to conductivity. The interaction between N-type and P-type materials is the foundation of many semiconductor devices. When N-type and P-type materials are brought into contact, a p-n junction is formed, which creates unique electrical properties. For example, a diode is a semiconductor device consisting of a p-n junction that allows current to flow in one direction while blocking it in the other. Semiconductor materials are essential for modern electronics and technology. Integrated circuits, ICs, which are made from semiconductors, have revolutionized computing and have led to the development of smaller, more powerful, and energy-efficient devices. The field of semiconductor physics and engineering continues to advance, enabling the creation of even more sophisticated electronic components and systems. What is properties of semiconductor material? Semiconductor materials possess specific properties that make them distinct and valuable for various electronic applications. These properties contribute to their ability to control and manipulate electrical current and voltage, forming the foundation for modern electronics. Here are some key properties of semiconductor materials. Electrical conductivity. Semiconductors have intermediate electrical conductivity compared to conductors, metals, and insulators, non-metals. Their conductivity can be adjusted by doping with impurities. Band gap. Semiconductors have a band gap, which is the energy difference between the valence band, highest energy electrons, and the conduction band, lowest energy electrons that can carry current. This energy gap determines whether a material behaves as an insulator, semiconductor, or conductor. Doping. Semiconductors can be doped with specific impurities to alter their electrical properties. N-type doping introduces excess electrons, while P-type doping introduces electron deficiencies, holes. Carrier mobility. The mobility of charge carriers, electrons and holes, in a semiconductor determines how quickly they can move in response to an electric field. Carrier mobility affects the material's conductivity. Thermal conductivity. Semiconductor materials generally have lower thermal conductivity compared to metals but higher than insulators. This property is important for managing heat in electronic devices. Optical properties. Semiconductors can absorb and emit light at specific wavelengths, making them essential for optoelectronic devices like light-emitting diodes, LEDs, and lasers. Photoconductivity. Some semiconductors become more conductive when exposed to light, as photons can excite electrons into the conduction band, increasing electrical conductivity. Temperature sensitivity. The electrical properties of semiconductors can change significantly with temperature, which can be both advantageous and challenging in various applications. Non-linear current-voltage relationship. The relationship between current and voltage in a semiconductor is not linear, allowing for applications like signal amplification and switching. P-N junction behavior. The behavior of P-N junctions, where P-type and N-type regions meet, leads to unique properties like rectification, diodes, and signal modulation, transistors. Semiconductor heterojunctions. Different semiconductor materials can be combined to create heterojunctions with unique electronic and optoelectronic properties. Tunability. The properties of semiconductors can be finely tuned through doping, temperature, and external stimuli like light or electric fields. Quantum effects. At the nanoscale, quantum effects become significant in semiconductors, leading to properties like quantum confinement and tunneling. Energy band diagram. This diagram visually represents the energy levels and band structure of a semiconductor, illustrating how electrons move between bands under different conditions. These properties collectively enable semiconductors to be used in a vast range of electronic applications, from simple diodes and transistors to complex integrated circuits, sensors, solar cells, and beyond. The ability to control and manipulate these properties has led to the rapid advancement of technology and the creation of the modern digital age.